lecture series on probability theory and stochastic process. In this lecture, we concentrate on properties of power spectral density. In previous lecture, what is the importance of a power spectral density was mentioned. Power spectral density plays a crucial role in estimating the average power of signals or random process generated. Okay, so if we know the mathematical expression for the signal, we can be easily able to estimate the average power, right? What is the expression? Let me just reiterate it. Average power equals to limit t tends to infinity 1 over t 2t minus t 2t x square of t dt. This is the expression for average power. Sometimes we also mention this as like this also, not always that it must be only 1 by 2t. Can also be taken sometimes like this 1 by t 0 to t x square of t dt also, because average power is the mean square. No, that also can be used. However, this requires the availability of a signal in time domain. X of t is represented in time domain. If the time domain representation is not available, we can estimate the average power in frequency domain also. Okay. The frequency domain representation of signals or processes requires much knowledge about Fourier transform. Okay. Fourier transform of any signal x of t. Why? Because I am calling x of t as a signal because one signal is a sample function in the random process. A random process is a collection of number of time varying waveforms. Each waveform is called a sample function, which generally refers one signal. So if x of t is a signal, its Fourier transform is given as x of omega equals to x of t into e power minus j omega t dt. Okay. So what we are currently mentioning, we want to estimate the power Pxx. What is Pxx? Pxx is the average power of a random process x. So it is generally defined as area under the power spectral density curve. Sometimes this Sx of omega is referred as power spectral density. Sometimes it is also referred as auto power spectral density. Okay, so what is this power spectral density Sx of omega? It is represented or given as Sx of omega equal to limit t tends to infinity 1, not 1, expected value of, okay, xt of omega mod square by 2t is the definition. This is the definition of our power spectral density. Power spectral density is the is useful in estimating the average power, and subsequently we are always using this notation for further purposes. So in this lecture, we concentrate on estimate the or proving the properties of power spectral density. Okay, so let us start here. First one. Power spectral density Sx of omega is always a non-negative quantity. Power spectral density Sx of omega is always a non-negative quantity, which is given as Sx of omega is greater than or equal to 0. So it does not require any much mathematical analysis to prove this property. It is known that Sx of omega equals to limit t tends to infinity, expected value of mod of xt of omega square by 2t. What is xt of omega? Xt of omega is the Fourier transformation of xt of t. Okay, so it is known Fourier transformation is always a complex quantity. It contains the real part as well as it contains the imaginary part also. But you can see that the definition for power spectral density is consisting of an absolute value. Okay, so as we are taking the absolute value, correspondingly, what happens is xt of omega mod square is always non-negative. Always it is non-negative. Even though Fourier transformation is a complex quantity, okay? Fourier transformation is even though a complex quantity, mod of is always non-negative. So once this is non-negative, automatically expected value of xt of omega mod square will be non-negative. Means positive. Non-negative means always greater than 0. Thus, we can say yes, x of omega always greater than or equal to 0. Always positive. That is the first one. Second one, most important property, the most important one, we call it as the extension of this is called as a Wiener-Kinchen relationship. This property says power spectral density and time average of autocorrelation function form a Fourier transform pair. This A stands for time average. E stands for statistical average. A of stands for time average. So the power spectral density and time average of autocorrelation function form a Fourier transform pair. In particular, okay, before this is applicable for stationary process, but for non-stationary process, let us first derive, then we continue for stationary. So for non-stationary, we will write this as Rxx of t comma t plus 2 better. So power spectral density and time average of autocorrelation function form a Fourier transform pair. So let us prove the property. It is known that Sx of omega equal to limit t tends to infinity, expected value of xt of omega square mod, right? The definition. Xt of omega mod square by 2. But what is xt of omega? Xt of omega is the Fourier transformation of xt of. We can write this as minus infinity to infinity x t of t e power minus j omega t dt. However, xt of t is the truncated portion. It is existing between minus t to t, and within minus t to t, it is defined as x of t e power minus j omega t dt. Okay, then let us continue. This is one. Similarly, I want conjugate. In the definition of your power spectral density, you have noticed there exists xt of omega mod square. So, which is generally is given as xt of omega into xt of omega conjugate. In such a scenario, we should be able to write what is the conjugate of this. Xt of omega conjugate will be equals to minus t to t. Same in the previous manner, x of t e power plus j omega t dt. However, to differentiate between xt of omega and xt star of omega, we use two different notations here. We put in this definition as x t1, g omega t1, dt1. To differentiate between those two, we can use this. Okay. So now let us substitute Sx of omega equal to limit t tends to infinity 1 over 2t outside first integration minus t to t x of t e power minus j omega t dt, then minus t to t x of t1 e power plus j omega t1 dt. Why this plus? Hope understood. We have taken the conjugate. Sometimes we can also mention or take this as T1, 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 and this as T2, T2, T2. It is not an issue because we are taking two different notations to discriminate between what is xt of omega, what is xt star of omega, right? Hope understood. X of t1 e power minus j omega t1 dt1. X of t2 e power minus j omega t2 dt. Also accepted. Okay, anything is okay. Now, so that is one possibility. Two. You can use either 2, 1, and 1, or use 2, 2, 2 everywhere also. It is not going to affect the solution or the proof. Okay, so Sx of omega equal to this. Further, Sx of omega equal to limit t tends to infinity 1 over dt. We have to apply expected value also because it is on the definition. Okay, okay. So minus t to t. Expected value is generally applied for random variables or random process. So x of t into x of t1. Okay, again, I am just separating the terms. One more minus t to t. Here it is e power minus j omega. This is t1 minus t dt1 dt. Right. So what do? We simplify further. This can be taken as limit t tends to infinity 1 over t minus t to t. Okay, this is e of x of t, x of t1. I can replace this as rxx, autocorrelation function of a random process. E power minus j omega t minus t, right? Here it is plus. So I need to mention this, right? Minus. So it should be t minus t because minus plus here, minus j omega t here, minus j omega t dt dt. There existed two integrations. So correspondingly, we have to add one more integration here, minus t to t dt1 dt. Now we take inverse Fourier transform on both sides. Apply inverse Fourier transform on both sides. So what it will be? 1 over 2 pi. Left hand side is Sx of omega. So minus infinity to infinity Sx of omega e power j omega tau d omega. This side limit t tends to infinity 1 over 2t minus t to t. Here it is rxx of t comma t1 minus infinity to infinity. Here it is 1 over 2 pi minus t. Okay, a second. That is mention one more time with a little clarity. Better. Okay. 1 over 2 pi minus infinity to infinity. Again, minus t to t e power minus j omega t minus t1 e power plus j omega tau d omega dt1 dt. Further simplification is like this. Okay, limit t tends to infinity 1 over 2t minus t to t r x of autocorrelation function t comma t1. Okay, minus infinity to, okay, this can be minus t, not infinity, minus t to t 1 by 2 pi minus infinity to infinity e power minus j omega tau plus t minus t1 d omega dt1 dt. This is the inverse of Fourier transform, right? 1 by 2 pi minus infinity to infinity e power minus j omega tau plus t minus t1 d omega can be inverse Fourier transformation, which is nothing but an impulse function. So limit t tends to infinity 1 by 2t minus t to t r x x of t comma t1 minus t to t del of, this can be taken as tau plus t minus t1 dt1 dt. Or subsequently, as the impulsive function is an even function, this can also be taken as del of t1 minus t minus tau also. It's also acceptable because it is an even function. Now you can replace that or this. Either of these things are okay. However, area under the impulse function is unity, right? Area under the impulse function is unity. So this will be equals to limit t tends to infinity 1 over t minus t to t r x x of t comma t1 dt. What is t1? Increment in time now. So let t1 equal to t. Because in the estimation of autocorrelation function, we have considered two random variables. One a time instant of t. Second one is a time instant t1. So two different time instants. So what I do now, time instant t1 is the increment of tau with t. So if this is replaced, this can be written as limit t tends to infinity 1 over t minus t to t r x x of t comma t plus tau. If you observe this carefully, this is the definition of time average A of. No, what is A of? A of equal to, this is definition. Limit t tends to infinity 1 over 2t minus infinity to the dt. This is definition of time average. Whatever function comes here, that comes here. So this will be equal to A of Rx x of t comma t plus tau. However, if the random process capital X of t is wide sense stationary, right? If X of t is wide sense stationary, if X of t is wide sense stationary, what is the meaning? Autocorrelation function is independent of time. Then it will be equal to R x x of tau. If you estimate this time average, its value will be one more time equal to Rx of tau. How this is done? How the A of Rx of tau equal to Rx of tau? So this can be easily proved. Whatever this term, A of Rx of tau equals to Rx of tau can be easily proved. Thus, the autocorrelation function and time average of autocorrelation function from a Fourier transform. If x of t is a wide sense stationary, then automatically we can extend this as like this. Sx of omega and time, autocorrelation function from a Fourier transform way. This is called as Wiener-Kinchain relationship. One most popularly sought theorem on relation. Wiener-Kinchain relationship. This property is much used in solving the other properties of power spectral density also. So let us go ahead with the subsequent properties. But further, what is the meaning of this? What is the meaning of Fourier transform pair? If you know autocorrelation function, you can estimate the power spectral density. This is very important. What is the advantage of this property? Minus infinity to infinity, Rx of tau, e power minus j omega tau d tau. It means power spectral density is the Fourier transformation of autocorrelation function, and autocorrelation function is the inverse Fourier transformation of power spectral density, which is given as like this: 1 over 2 pi minus infinity to infinity Sx of omega e power j omega tau d omega. This is very important. These two expressions are very, very important in solving problems. So let us go with the another property here. It says power spectral density is an even function of omega. Sx of omega equals to Sx of minus omega. Okay, even function. So how to prove this? From the Wiener-Kinchain relationship, just we have proved here. What is the definition of power spectral density? And I mean, even no need to use that also. We can directly substitute. But let us see. Okay. Number of ways to solve this property also. Fourier transformation of my Sx of omega. This is equal to Sx of Rx of, not Sx of omega. It is the Fourier transformation of Rx of tau. So Rx of tau, which is given as minus infinity to infinity Rx of tau e power minus j omega tau d tau. Now what I do, I go for second, Sx of minus. So minus infinity to infinity Rx of tau. Here it is minus. So minus j minus omega tau d tau. S x of minus omega equal to rearrange minus infinity to infinity r x of tau e power minus j omega minus tau d. This minus omega minus has been taken. Let minus tau equal to u. So d tau equal to minus d. Of course, limits also are going to be changed. Then you can write as Sx of minus omega equal to initially minus infinity to infinity Rx of minus u, y minus u, minus tau equal to u. So tau equals to minus u, e power minus j omega u minus d. This is minus. So limits can be interchanged again. This is plus, this is minus. Again, minus 2. Oh, clear? Okay. Rx of minus u e power minus j omega u d. But from the properties of autocorrelation function, we know autocorrelation function is an even function. That is, Rx of minus u is equals to Rx of u. Autocorrelation function is an even function. So what happens here? S x of minus omega equals to minus infinity to infinity Rx of u e power minus j omega u du. U is a dummy variable. It is almost similar to Rxx of tau e power minus j omega tau d tau, right? U is a dummy variable. So this is equivalent to, you can write as Rxs of tau e power minus j omega tau d tau, which is nothing but Sx of omega. Thus, autocorrelation function, power spectral density or auto power spectral density is an even function of V. Okay. Actually, there are a number of ways to prove these properties. Even by using the definition of the power spectral density also, you can prove the same, right? Why? Because power spectral density contains mod of xt of omega square. So as there exists the modulus value, that is also can be one way to prove this. So let us go for the subset properties. This states that autocorrelation function is, sorry, power spectral density is an even function. Next, fourth one. If okay, better first of all, let the if x of t random process has power spectral density Sx of omega, then derivative of random process will be having power spectral density omega square into Sx of omega, right? For x of t, Sx of omega, for x derivative, this dot indicates derivative. It means like this, dx of t by dt. This means, okay, its power spectral density will be this. Okay, so that is solve this property by using the proof definition of PSD. What is definition? Sx of omega equal to limit t tends to infinity, expected value of xt of omega mod square by 2t. What is xt of omega? Fourier transformation of xt of t, right? So in our case, what is required for us? We want what is the power spectral density of derivative of the random process. So in such a case, limit t tends to infinity, it can be taken as s xt of omega bar square by 2t. This bar indicates derivative. See, derivative of Fourier transform. X of t as x of omega. So xt of omega bar is the Fourier transform of derivative. That is our interest now. So from the properties of Fourier transform, we know xt bar of differentiation in time domain equals to multiplication by j omega in frequency domain. That is differentiation in time domain is equals to multiplication in frequency domain. So we can replace this as what is required. S x of omega equals to limit t tends to infinity, expected value of mod of minus j omega xt of omega square by 2t. Because of this mod operation, that is its absolute value, what happens? Omega square will be the outside expected value. So this will be equals to omega square into limit t tends to infinity, expected value of xt of omega mod square. Right? What happened to minus j omega? The mod operation has removed minus j omega. It is omega square. So what is this term? This term is, of course, Sx of omega. So Sx of omega equal to omega square into Sx of omega. This is the power spectral density of random process x of t. This is the power spectral density of derivative of random process x. Dx of t by. Okay. So these are the properties. Then we have a few more properties. 51, which states we can estimate the average power of a random process from its power spectral density, or you can write 1 over 2 pi minus infinity to infinity xx of omega d omega equal to e of x square of t, mean square value of power equal to r x x of z. So average power of the signal is the autocorrelation function at tau equal to 0. That is 1, which is already known. The properties of autocorrelation function, we know this already. Average power of a signal is the value of autocorrelation function at the origin, which is equals to this. So that is defined. Our autocorrelation function is the inverse Fourier transform. Okay. Autocorrelation function is the inverse Fourier transform of power spectral density. What it means? This is equals to 1 over 2 pi minus infinity to infinity Sx of omega e power j omega d omega, right? Now I put R tau value 0. The tau value 0 means Rx of 0 equal to 1 over 2 pi minus infinity to infinity Sx of omega d omega, because tau value 0. So exponent becomes 1, which is nothing but mean square power. That is what our interest in the beginning also. We told why we need power spectral density. Power spectral density is required to estimate the average, which is nothing but Rx of 0. Okay. So power spectral density is an even function. The average power of a random process or a signal can be obtained from the area under the power spectral density. And last one, of course, Sx of omega is always a real quantity. This is self-explanatory. It is known that Sx of omega equals to limit t tends to infinity, expected value of xt of omega mod square by 2t. Xt of omega mod square is always real, right? Is always real. So automatically, okay, now, why? Because of presence of the absolute value or mod value. So as xt of omega mod square is always real, correspondingly, the power spectral density is also always real. So these are the properties of power spectral density. Keep on learning. Mathematical aspects are very much needed, in particular for communications and signal processing domains. Without knowing how to estimate the power of a signal, we cannot evaluate the performance of a communication system. Why? Because for estimating the signal to noise ratio, we should know the average power, either in time domain or in frequency domain. That is what we have discussed in this lecture. Thank you. Thank you.